Okay, so hi everybody. So it's actually, let me just close the door. So it's lecture 13. And so okay, what did we do last time? Okay, I don't know what that is. So last time we discussed a number of very important concepts that are quite central to what we're going to be doing throughout the course, actually. So we said what an isomorphism is. So let me just remind you that's a linear transformation between two vector spaces that is one-to-one and onto. And then we talked a lot about bases of a vector space. So basis, let's call it script B is a list of vectors. So basis of a vector space V satisfies two properties, that its span is equal to V and it's linearly independent. And then given a basis, there was a very important operation, which is actually a linear transformation associated with it, which is the coordinate mapping. So if V has a basis with n vectors as above, then the coordinate mapping of a vector is a vector in Rn for a vector x. Excuse me? Sorry. Okay. For a vector x in V, which is expressed as a linear combination of the basis vectors. And this is a, because it's a basis, this is a unique linear combination. And the key thing in the coordinate mapping is that the number of entries in this vector is equal to the number of elements in the basis. Right. So in particular, this vector it lives in Rn, and this coordinate mapping is a map. So let me actually draw a diagram. So the picture is that there's a vector space V. It has a basis, or we've chosen some basis of n vectors. And then there's this linear transformation that takes V to Rn. And this is the coordinate mapping. And this is always an isomorphism. So it has an inverse, which is this thing that we call PB. Okay, so this is related to both. This is related to both the concepts of basis and isomorphism. And okay, and the upshot of all of this is that there's something which I call the correspondence principle, which says that because this is an isomorphism, every linear dependence in V is reproduced in Rn and vice versa. So every so I mean, there are many ways to think about this intuitively. So one sort of way to think about this is that what's happening up here is happening in a so-called abstract vector space. And what's happening here is happening in a concrete vector space. And this kind of reasoning comes up all the time in higher level math. And you may be surprised, but the words people use in graduate or higher level math to describe this often is upstairs and downstairs. These are just intuitive words, but you can think of what's happening upstairs as being somehow higher level or more abstract, and what's happening downstairs as being concrete. And what this correspondence principle does is it tells you that once you have a basis above, then you can turn everything that's happening upstairs into something that's happening downstairs. And you can, the upshot of all of these things together is that you can solve problems in V by turning them into problems in Rn. So can translate problems and also even theorems, which we'll see today, in V to Rn and vice versa. Okay, so given an isomorphism, you can climb up and down the stairs basically. Okay, somebody asked what is PB, so let me just remind you. So PB is, PB of a coordinate vector C is the vector C1 B1 plus all the way to Cn Bn, and PB is a linear transformation from Rn to V, and it's the inverse of PB is the coordinate mapping. Okay, that's the relation between these things. So that's a brief recap of what we did last time. Okay. Any questions about the recap?
So is PB just a matrix formed by the vectors B1 through Bn?
Great question. So the question was, is PB a matrix? Okay, so that's a good intuitive way to think about it, but actually it's not a matrix. Why is it not a matrix? So let's look at this B1 through Bn, right? Now suppose V was, let's say, the space of polynomials of degree 3. Would that be a matrix? So for example, let's say B1 is this polynomial, B2 is this polynomial, B3 is this polynomial in P2, right? Can you make a matrix out of those?
No, I
No,
guess.
you can't, right? Matrices are arrays of numbers. So you can't put abstract vectors in a matrix. So the answer is no, because it's not an array of numbers. However, this is a good intuitive way to think about it. It does behave like that, but it's going between Rn and V, not between Rn and some other Rm. So it's not a matrix. Okay.
I actually have a question regarding that last question.
Yep.
So would you describe PB as like a set of the linear combinations then, or like?
No. So PB, you just describe it in words. It's this linear transformation here in the box. It takes a vector in Rn, which is just, which is just an array of numbers. And it spits out a vector in V just by forming the linear combination.
Okay, thank you.
Yep. Any other questions about this?
Is the B like the same thing as the like fancier B for basis?
Yes, sorry. So these are all fancy Bs. So these should all be, these are all the bases, yeah. I don't know if putting this makes it fancy, but yeah. Okay. So today what we're going to do, so I said we can translate problems and theorems in V to problems in Rn, right? So last time we actually did translate we translated a problem about linear independence from P2 to R3. And today I'm going to show you how to translate some theorems. So what are we going to do today? I'm going to talk more about the dimension of a vector space. I'm going to prove some nice theorems about it, like the too many vectors theorem and so on. And then I'm going to extend the correspondence principle to linear transformations. So right now, the correspondence principle only talks about vectors living in V, right? And it turns them into vectors in Rn. What about linear transformations? Well, it turns out there's a way to do that too. And then finally, I'll make some sort of general comments regarding this section of the course. This is historically the most challenging part of the course because it's the most abstract. And that's sort of a new thing for many people taking linear algebra for the first time. So I'll tell you why this abstraction is worth it at the end of the lecture. So let's start by talking a little bit more about dimension. So, okay, recall the definition, or maybe let's state the definition. The dimension of a vector space V is the number of elements in a basis of V. So this is denoted dim V. Okay. Now, there are some vector spaces. So for example, the dimension of Rn is n. The dimension of P2 is 3 because the basis for it has 3 elements. And then we need one more thing. The dimension of F, this vector space of all functions from real to real, this actually doesn't have a finite basis. There's no finite set of functions that span all of them. So we're just going to write this as the dimension equals infinity. And we're actually not going to find a basis. So if it doesn't have a finite basis, we write dimension as infinity. Okay, so when you see this definition, you should be a little bit suspicious because it says the number of elements in a basis, right? And right now it could be that you have 2 different bases with different numbers of elements. So this doesn't seem to be well defined a priori, right? So the first theorem I'm going to prove is that all bases of of a vector space which has a finite dimension, all of them have the same number of elements. Okay, so let's state that as a theorem. So let's see, how do I want to state that?
Professor?
Yes?
This might be a dumb question. I'm a little bit confused by what you mean by it might seem like a little bit suspicious right now because we have 2 possible bases. With
yeah. So the question is, this says, really the definition says in any basis, right? So the question is, how do we know that all bases have the same number of elements? Does that make sense? There's nothing in the definition that says that they all have to have the same number of elements.
Yes, that makes sense. Thank you.
Right. So let's now show ourselves why indeed they all have to have the same number of elements. Okay, so here's a theorem. This is like the too many vectors and not enough vectors theorem in V. So suppose you have suppose a vector space V has a basis let's call it B1 through B M. So it's called as B. Okay, so it has some basis. And now suppose you have a bunch of other vectors, V1 through Vn, that lie in this space. And there are two things. If the vectors are linearly independent, then the number has to be less than the dimension of the space. And if they span, then the number has to be at least the dimension of the space. Okay, so this is the same as it's the same theorem as the too many vectors, not enough vectors theorem. In that theorem, I said, I proved the contrapositives of these statements. I proved that, well, if there are less vectors in the dimension, then you cannot span. And if there are more vectors in the dimension, then you cannot be linearly independent. Those statements are logically equivalent to what's written here, right? That if they are linearly independent, then there must be fewer vectors in the dimension. So again, this, according to our definition, this means that the dimension of V is equal to M. So that's the statement. So any questions about the statement before I get to the proof? So I'm going to prove this using the correspondence principle, and just to show you how powerful this isomorphism business is. Somebody said, what if they span and are linearly independent? Okay, that's a good point. So C, we might as well write that here. If both are true, so I mean, C is just a consequence, right? So if V1 through Vn is a basis of V, then, well, then it has to be linearly independent and span, then N equals M. And that, that actually answers the question of why all the bases have the same size. But C just follows from A and B. Okay, so let's prove this.
Oh, sorry, I want to ask a question.
Yes, please.
Yeah, so because we can no longer use pivots, so how do we concretely prove that U and Vn are linearly independent or that they span V?
Oh, I'm not asking to prove that they are linearly independent. I'm saying if they're linearly independent, then there must be fewer of them than the dimension.
Oh, okay.
Right, so there's a if then in all of these.
Oh, okay, that makes sense. Thank you.
So let's do the proof of A first. Well, we should use the core. Okay, I won't draw it here. So I have that V1 through Vn are linearly independent in V, right? But now, according to the correspondence principle, there's a mapping from upstairs to downstairs, and the downstairs is Rm because the dimension of V is M, right? Given by the coordinate mapping with respect to this basis, and it has an inverse as well. So if I apply the correspondence principle, what does this imply about the coordinate vectors of these? So I can take all of these vectors and just now look at their coordinate vectors with respect to the basis.
They would also be linearly independent in V.
Almost. You said they'll be linearly independent in V. That's not true because they're not in V.
In Rn, they'll be linearly.
In Rm, yeah. Okay. Okay, so now you have n vectors that are linearly independent in Rm. Can you say anything about n and m?
We can say that n must be less than or equal to m.
Yeah, just from week 2, from the good old too many vectors theorem, right? this implies n is less than or equal to m. And that's it. So you didn't have to do any extra work. That's the beauty of the correspondence principle. We are now going to, we don't have to throw away everything we did earlier, right? So now let's prove the item B. Item B is just, okay, so V1, so V1 through Vn span V. And now again, by the correspondence principle, you get that the coordinate vectors span Rn, or M actually in this case. And then by the not enough vectors theorem, from week 2, you get that n is at least m. Okay, so it's not hard once you have the isomorphism. All the action is in this correspondence principle step. I mean, these are actually double arrows, although we're only using one implication. But then, this implication implies something about n and m. And then item C is just kind of, it follows from A and B, right? So that's the proof. And that gives the answer to the question on the previous slide. Well, just by part C of the next theorem.
Professor, should the too many vectors and not enough vectors be swapped?
No. So the too many vectors theorem says if n is bigger than m, then they cannot be linearly independent.
Oh yeah, you're right. Sorry.
I agree. No, it's a good question. It's a little confusing. I've negated, I've taken the contrapositive of the original statement here, right? Logically, too many vectors, there are two ways of saying it. One is if n is bigger than m, then you must be dependent. But that's the same thing as saying if you're independent, then n has to be less than or equal to m.
Can you go over the whole upstairs downstairs thing one more time, please?
Yeah, the upstairs downstairs thing is that there's a vector abstract vector space above, there's a Rn below, where the n is the number of elements in the basis, right? So this n is the same as this n, which is the dimension of V. And the point is that because this coordinate mapping is 1-to-1 and onto, because it's an isomorphism, every statement in linear algebra that's true upstairs, the corresponding statement is true downstairs for the coordinate vector. So another way of thinking about this is that upstairs you have things like polynomials, some kind of abstract vectors, and down here you have names of things. Don't subscribe to this if you don't like it, but some people prefer this. And what this is saying is that whatever's going on with the things upstairs has a shadow downstairs, and exactly the same corresponding thing is going on downstairs.
Okay, thank you.
Yep. Any other questions about this? Okay. And now I want to say one last important thing. So what did we achieve? That all bases have the same dimension. Okay, that's nice. And along the way, we proved the too many vectors, not enough vectors theorems as well. I want to prove one more thing, which has kind of been implicit in the last couple of lectures anyway. So that is that, so we've defined dimension for a vector space, right? It's just the number of vectors in a basis. And if that number is finite, it doesn't depend on the basis. That's what this proves. Now that's just a pair of numbers, right? And yeah, and then okay, so the thing I want to prove is that this number is actually all you need to know about a vector space to know about its linear algebraic structure. So here's a theorem. The theorem is if the dimension of V is equal to the dimension of W for two vector spaces and both are finite, then they're isomorphic. Okay, so this one number is all you need to know in order to figure out whether there's an isomorphism. And isomorphism is very nice, right? Because it allows you to turn problems in one space into problems in another space. So the proof of this is actually quite nice. There are many proofs of this. Let me give you, I'll give you one of the proofs that uses composition, which is something we'll be using a lot later. So here's a proof. So let B be a basis of V. Okay, so and we've assumed dimension of V is n, right? So let's write this as n actually. Some finite number n. And let C be a basis of W. So I have these two spaces. I have V, it has its basis B. I have W, it has its basis C. Sorry, that's not the right C. Okay. Now, well, what do I know how to do with bases? I know how to actually construct isomorphisms between V and Rn, right? So there's an isomorphism between V and Rn, namely the coordinate mapping, which is also PB inverse, right? That's an isomorphism. So this is isomorphism. It's one-to-one and onto. Now, what about this other vector space W? Anybody see an isomorphism between Rn and W?
PC inverse.
Okay, yeah, so you could do PC inverse if you wanted to do the same thing. And if you wanted to go the other way, what would you do?
Use T, the translation.
T is not defined yet. We're trying to find the T.
Just PC?
Just PC. So here are some simple facts about isomorphisms. The inverse of an isomorphism is an isomorphism. That's because an invertible, I mean, well, its inverse is the original transformation. Okay, so now I'm going to do kind of a cool thing. I want to find an isomorphism between V and W, right? Can anybody think of how to make one out of what we have on the table here?
PCO-PB.
Close. You said PC of PB. That's not quite right because remember PB goes this way, right?
Right, sorry, PB inverse.
Yeah, PC of PB inverse, right? So if you wanted to follow the arrows, what you could do is you could follow, first you could do this, and then you could do this arrow, and then you would go from V to W, right? So let T be PC of PB inverse.
Okay.
Okay. And now the point is, this is another fact that you've kind of seen already with matrices. If you multiply two invertible matrices, you get an invertible matrix, right? Well, the same thing is true of isomorphisms. If you take two transformations that are one-to-one and onto and compose them, you get another isomorphism. So composition of isomorphisms is an isomorphism. And that's it. That T is an isomorphism. So T equals PC of PB inverse. Now this goes from V to W via Rn, but it goes from V to W is an isomorphism. That's it.
I have a quick question about the proof we just did.
Yep.
This may seem really simple, but why do we do the order, the transformation of PC then PB? Like, why isn't it the other way?
Right. So this goes back to what we did about composition of linear transformations in the first place, right? Because let's say you have a vector. So PC of PB inverse means, what does it mean? Maybe I'll write it here. T of a vector X is equal to PC applied to PB inverse applied to X, right?
Oh yeah.
So now that makes sense, right? Because this X lives in V. This whole thing, where does this live?
In V, I mean Rn.
Rn. And then when you apply PC, you get something in W.
Right. Yeah. Thank you.
Good question. Okay, so that's it. If the dimensions are equal, they're isomorphic. And remark, the converse is also true, and that's even easy. That's easier. I'm not saying this was easy. That's like very concrete. The converse is also true. If two vectors are, so if V and W are isomorphic, then the dimensions have to be equal. Okay, so that's all I want to say about dimension for now. And this is how we think of dimension. So earlier in the course, we were, we talked about two-dimensional objects, three-dimensional objects, etc. But dimension really is the number of elements in a basis. That is, in the beginning of the course, I said this course would teach you what thinking in high dimensions means. This is the definition of high dimensions. There's actually no more fundamental definition than this. It's a number of elements in a basis.
Can I ask a quick question?
Yes. Mm-hmm.
So I thought that we got like the coordinate mapping from knowing what an isomorphism is, but here it feels like the other way around. We kind of define isomorphism from coordinate mapping. So kind of which one should come first?
Yeah, well, so it's a good question. So we got this T out of PB and PC, right? But we got PB and PC from the coordinate mapping. And that we did in the last lecture, right? Or in the summary here, right? So the coordinate mapping, we started with two isomorphisms, which were the coordinate mapping and inverse coordinate mapping. And then we composed them to create the new isomorphism. Does that answer the question?
Yeah, thank you.
Yeah. Okay. So that is the first thing I want to do. Now, the second thing I want to cover is the correspondence principle for linear transformation. This is just a fancy name for the matrix of a linear transformation, but in more generality. And in the book, this is in section 5.4. So I don't like the way the book is organized for this material, so it may appear that I'm jumping around, but I think this is a better way to present it. So, rather than do this completely abstractly, so many people mentioned in the feedback that the lectures were too abstract, I'm going to do a running example first. So here's a running example. Let's consider the following linear transformation. T going from P3 to P2. So that's polynomials of degree at most 3 to polynomials of degree at most 2 by T of a polynomial is you take the second derivative of the polynomial and multiply it by T. So for example, let's just to make sure we understand this, let's evaluate this on a particular polynomial, T of the polynomial 1 plus T squared. What would that be? Well, it would be T, the variable T, little t, times the second derivative of the polynomial 1 plus T squared. What's the second derivative of the polynomial 1 plus T squared?
1.
It's actually 2. Because the 1 goes away and the derivative of T squared is 2T, and you differentiate that one more time, you get 2. So this is T times 2. So it's just the polynomial 2T. Okay, so that's a linear transformation. You can check that. That's not what I want to emphasize, so I'm not going to check that right here. But it kind of makes sense because differentiation is a linear transformation and multiplication by the variable T is a linear transformation. So this is just the composition of those, so it should also be linear.
Can you explain how 1 plus T squared is in like P3 and then 2T is in like P2?
Sure. So P3 is, whoa. Okay. P3 is a set of polynomials of degree at most 3, right? So what's the degree of 1 plus T squared?
2.
Yeah, so in particular, it's degree at most 3. So it's a valid element of P3. Is that okay?
Yeah, thank you.
Okay, so this is, somewhat unfamiliar looking linear transformation. So the question I want to ask is a motivating question. Can we represent this by a matrix? So previously, before the midterm, we saw how to represent linear transformation between Rm and Rn as a matrix, right? And that was very nice because then you could, it's very concrete. You can do row reduction, et cetera, et cetera. So what do we even mean by this here? Well, let me draw a diagram to show you all the spaces that are involved. So first there's P3. And we have a linear transformation from P3 to P2, right? Now, right before this, and even in the last lecture, we learned how to represent P3, how to at least think about vectors in P3 as being vectors in some Rm, right? So which Rm was, so how do we do that actually? Well, we chose a basis for P3. That's a basis. And now which Rm is that going to be isomorphic to?
R4.
R4, because there are 4 elements in the basis. So there's a map from P3 to R4. And that map is the coordinate mapping with respect to the basis B. Similarly, on this side, we had another basis. Let's just use the standard basis. And what is P2 isomorphic to?
R3.
What did you say?
R3.
R3, because there are 3 basis elements. And here I'm going to write the isomorphism going up. You'll see in a moment why, and let's call this is PC. And just to make all of this concrete, P3 contains, my input. This is the domain of T, so this contains my polynomial Q, right? So for example, in this example, it's 1 plus T squared, right? P2 contains T of Q, which in this case is what?
2t.
2t. And now we've already thought about how to express these input and output vectors as vectors in R4 and R3, right? So in R4, the vector that's going to be sitting there is the coordinate vector of Q with respect to B, which is what?
1, 0, 1.
0.
1, 0, 1, 0. And what's sitting in R3 is going to be the coordinate vector of the output, TQ, T of Q, with respect to the output basis, C. So I'm distinguishing now. This is the input basis. So basis of the domain, and this is the output basis. So what's the coordinate vector of TQ?
0, 2, 0.
0, 2, 0. Okay, so it looks like, there's this transformation going on upstairs. And if you look at the input, it has this shadow downstairs. And you look at the output, it has this shadow downstairs. So you can ask this question, is there a matrix relating these two things? So really the question is there a matrix that directly maps the coordinate vector of the input to the coordinate vector of the output? That's what this question should mean in concrete terms. So the question is there a matrix A? And what dimensions would the matrix have?
4, 3.
3 by 4, right? Because you have to multiply on the right.
Oh, yeah.
Such that what? Such that the matrix does to the coordinate vectors what the transformation does to the vectors. So we want A of the coordinate vector of Q to be equal to the coordinate vector of T applied to Q in the output basis. Okay, so this is a very important equation. And let's stare at it for a while because it's a bit more abstract than things we've been doing so far again. I'm just asking a question. Is there a matrix that does this, right? Is there a matrix that does to the shadows what T does to the original vectors upstairs? I don't know yet. We'll see in a moment that there is one. But any questions about the setup? This T looks like a J. It should say T. I mean, it would be nice if there was, right? Because then I could understand this linear transformation as, in terms of this matrix, which is a more concrete object. So some people asked a very good question in the chat. So could you ask it in speaking also?
Wait,
Okay, well,
do you mean P3 and P2?
Can you say it again?
Do you mean the one with P3 and P2?
Yeah, the one with P3 and P2.
Oh yeah, I was just wondering if P3 and P2 could be isomorphic.
Great question. So in this setup, this is an isomorphism. This is an isomorphism. And the question is T an isomorphism? Anybody know the answer?
I thought it wouldn't be.
You're right. Why wouldn't it be?
Because that would contradict the theorem we saw before.
Exactly. The theorem says that, vector spaces are isomorphic only if they have the same dimension. I mean, the converse says, right? If V and W are isomorphic, they have to have the same dimension. And these don't have the same dimension. So T is not an isomorphism. The isomorphisms are what's allowing us to, relate everything to things happening in Rm. But the T itself is not an isomorphism, and it doesn't have to be. Okay, so let's answer this question. So what's the key observation? Key observation is something we already did in week 3. Key observation is that T is completely determined by what it does on the basis B. Right? So this basis B has 4 vectors. So let's give them names, right? Okay. So let me just write it out, right? So T of 1 is D times D by dt squared of the polynomial 1. Anybody can see what that is?
0.
0. Because the second derivative of 1 is 0. T of the polynomial T is T times second derivative of T, which is also 0. T of T squared is T times the second derivative of T squared. And now something interesting happens. Anybody see what this is? So this is T times, what's the second derivative of T squared? 2. So it's 2T. And now T of T cubed. What's that?
3t squared. Or 6t. 6t squared.
Yeah, so it's T times the second derivative of T squared, which is 3 times 2 times T. So it's 6T squared. Okay. So now we figured out what T does on this basis B, the input basis. Okay, but now I can express any vector in P3 as a sum of the, uniquely as a linear combination of these input basis vectors, right? So now if I have some other vector, let's call it A0 plus A1T plus A2T squared plus A3T cubed. Well, okay, by linearity, that's just a linear combination of these vectors, right? No, not A0, sorry. T of 1. Or let me move this so I have no space to write it. Okay. Any questions about that? That's not something new. Okay, now I'm going to do something sneaky. I'm going to take coordinate vectors everywhere. So this vector on top, right? The thing I put in square brackets, which vector space does it live in?
P2. Wait.
P2.
Yeah.
So we take the coordinate vector of this with respect to C. And now that's also a linear transformation, right? Taking a coordinate vector is a linear transformation. So by linearity, I can also do this.
Sorry, how does that live in P2 if the degree is 3?
No, the T of this lives in P2.
Oh, I see. Thank you.
Yeah, so the inner thing lives in P3. The T of it lives in P2. Right? Okay, but now this is kind of cool, right? Because where do these coordinate vectors live? They live in R3. So can you write this as a matrix vector product?
Would you go all the A's in a column?
Yeah, exactly. And now you can legitimately, well, okay. I mean, okay. Let's actually write down what these T's are, right? So this is A0 times the coordinate vector of 0 plus A1 times the coordinate vector of 0 again plus A2 times the coordinate vector of 2T plus A3 times the coordinate vector of 6t squared. Sorry, maybe I'll move this just to make, maybe I'll just write it again just to make it clear. This is A0 times the coordinate vector of 0 plus A1 times the coordinate vector of 0. So, right, these are just the outputs I calculated on the left-hand side here. Plus A2 times the coordinate vector of 2t plus A3 times the coordinate vector of 6t squared, which, just to be very explicit, let's write it out. This is A0 times 0, 0, 0 plus A1 times 0, 0, 0 plus A2 times 0, 2, 0 plus A3 times 0, 0, 6. And now, as you're saying, I can put this in a matrix. And now what's left here is A0, A1, A2, A3. Okay. But now, okay, I mean, this input, so let's call this vector Q, which lives in P3, right? Did I assume anything about Q? No. Every vector in P3 looks like that. And in fact, that's its expansion in the basis, right? So this vector, this vector appearing here, what is it in terms of Q and in terms of the items appearing on this diagram here? Like conceptually, how would you describe this vector?
Is it the coordinate vector of Q?
Yeah, it's the coordinate vector of Q. So this is some matrix A, so let's call this matrix A times the coordinate vector of Q in the input basis. But this is exactly what we wanted, right? We wanted that for every Q, there should be a matrix that maps the coordinate vector of the input to the coordinate vector of the output, and this does exactly that. So actually, we solved this example. So therefore, T of Q in the output basis equals this matrix. Well, let's just call it A times Q in the input basis for every Q in P3. And so we solved the problem in this example. So now the punchline, or I guess mini punchline, I guess is not such a big one, is that this always works. This is the same reasoning we did for the standard matrix, just in a bit more generality, because now the bases are, could be different from the standard basis, and the vector spaces could be different. Before I state the general theorem, any questions about this example?
Is A sort of a type of basis then?
A is not a basis. A is a matrix representing the linear transformation. So a basis is a set of vectors, right? This A is a matrix, first of all. It's not a set of vectors, but what its job is not to span the space or be linearly independent. Its job is to represent the linear transformation T. To do what we wanted in this picture here, this A in the bottom. Any other question?
So is the key observation theorem we can directly use?
I'm going to state the theorem in the next slide.
Okay, thank you.
So the general theorem is if T is a linear transformation from V to W, and you have two bases of the input and output spaces. So B1 through B, let's say M is a basis of V, and C equals C1 through Cn. These may not be the same. Is a basis of W. Then this matrix. So it's, what did we do in this construction, right? What are the columns of this matrix? Well, they're the images of the input basis expressed in the output basis. So what are the dimensions of this matrix? Oh, sorry. Let's see. I wanted I'm sorry. I wanted to be consistent with what we did earlier. So let me change these M and N. The input basis, the input vector space has dimension n. The output has dimension m. So what are the dimensions of this matrix? How many columns are there?
They're M columns?
There are n columns, right? Because there's one column for every basis element of V. And how many rows are there?
M rows, M.
M, because the number of coordinates in a coordinate vector of an element in W is M. So this is an M by N. Satisfies A times, let's say, X in the input basis equals T of X in the output basis for every X in V. That's a general theorem. And so this is denoted also T superscript on the right B, on the left C. So this is for input and output basis. And this is, so this is called a matrix of T relative to B and C. And this notation is kind of nice because this notation, what does the equation look like in this notation? It says if you take this T subscript B and left subscript C and multiply it by X sub B, then you just get Tx sub C. So it's actually easy to remember if you use that notation. So these are the same fact. Okay. So that's the general theorem, and the proof is just what I wrote on the slide. You express an element of the domain in terms of the input basis, or use linearity, hit it with T, and that's it, you're done. So any questions about this statement?
Okay.
Sorry.
Go ahead.
Okay. For the example you gave us, the conclusion is that for every Q in P3, we have that statement, but this is only based on this specific example of like 1 plus T squared.
Yeah, this is for this particular T, right? Yeah, but the point is that this thing I did on the right-hand side, that works in general. I didn't use anything specific. I mean, this particular matrix, of course, depends on the particular transformation, but this sequence of steps that I did on the right-hand side, I could do this for any transformation.
Okay.
And if you do it for any transformation, you get this theorem.
Okay, thank you.
Could you explain again how those two statements are the same, or like that notation again?
Oh, I'm just denoting this as A, right? So they're literally the same statement.
Okay.
Yeah. This is a nice notation that the book uses. We'll also be using that. Just it's good because it forces you to be mindful of the bases, right? And the bases are important. If you change the bases, you end up changing the matrix. We're going to talk a lot about that later. This is matrix of T relative to the bases B and C. That important to remember what the bases are. And I should say this is actually includes a concept you did before the midterm, which is the standard matrix of a standard matrix of a linear transformation. So here's a remark. If you take V equal to Rn and W equal to Rm, and both bases equal to standard, so you could do that, right? That's a special case of this. Then the linear this thing is just equal to the standard matrix, which is, if you recall, just T of E1 up to T of En. And now, so why is this the same as what's written in the theorem? In the theorem, it looks like you're taking coordinate vectors of the outputs with respect to the output basis. But in the standard matrix, it didn't look like you were taking coordinate vectors, right? So why are they the same?
Wouldn't the weights be 1? Or
Which weights?
like if we took the coordinate vectors of TE1, wouldn't it just be TE1?
Exactly. Vectors in Rn are just coordinate vectors of themselves. Okay, that got a little tight. Let me make some space. So that's the same thing. It's just a generalization of the same concept. Okay, so what's the point of doing this? Well, the point is you can transfer again problems and theorems. So upshot, can transfer problems and theorems between VW and Rn, Rm. So in particular, the correspondence principle that I want to highlight is, I mean, really, this is what I'm going to call the correspondence principle for operators, but it's just taking a matrix of a linear transformation, right? So T of X equals Y in V and W if and only if, when you take the matrix with respect to bases, in Rn, Rm. So let's do some examples of that. Let's do a problem. Okay, first let's do a problem. The problem is going to be related to this example. Okay, so let's just write that again so remember what it is. You have this linear transformation T from P3 to P2 by T of Q is equal to T second derivative Q. And the question is, find bases of the kernel of T, which is, remember, it's a set of polynomials in the domain, so that T of Q is equal to 0, and the image of T, which is the set of polynomials in the, let's call it R, in the range, so that T of Q equals R has a solution. Now this might, you might be a little scared by this, right? Because this is some weird linear transformation. And maybe these concepts are not so familiar, right? So these are now subspaces of V and of W. So let's call these problem A and B. And you know, it's not, you can't row reduce them, right? They're dealing with some abstract vectors right now. But now what's the idea? Well, the idea is to use the matrix, right? So I know that T of Q, the coordinate vector, is equal to this matrix A times the coordinate vector in the input basis for a very concrete matrix. This matrix is not scary at all, right? And so what's the upshot? Well, the upshot is by this correspondence principle, I can translate my problem into a problem about this matrix. Right? So let's solve problem one. So step one, well, let's do it in the next slide so that everything is in one slide. Well, okay, let's just do it here. So step one is to observe that, well, you know, when is a vector in the kernel of T? Well, that's true if and only if, according to the correspondence principle, only if the coordinate vector of Q is in the, well, okay, so, okay, maybe I'll skip, I won't skip the step. Being in the kernel of T is the same thing as saying T of Q is 0, right? In V, or I guess in W, because T of Q is in W, in P2, right? That's the definition. But now by the correspondence principle, that's just an equation about a linear transformation in some vectors. So this is the same thing as A times the coordinate vector of Q is equal to the coordinate vector of 0 in R3. Right? That's what this says. Statements about linear transformations are exactly translated when you go upstairs and downstairs with these isomorphisms. So then this is the same as what? In terms of concepts before the midterm.
The null space?
The null space, yeah, the same thing as saying the coordinate vector of B is in the null space. So that means if I find the null space of this matrix, I will find the coordinate vectors of everything in the kernel of T. And then I can just translate them back. So step one is translate the question to, you know, Rn. Step two is solve the question in Rn. So in this case, we're in R3, right? So the null space of A now lives, oh, sorry. The null space of A lives in R4, right? So, okay, we know how to find, I'm just going to do row reduction. And I don't want to do it again in front of you because I don't want to emphasize that. So if you do row reduction, give that the null space of A is the span of these two vectors. I did it earlier, 1, 0, 0, 0, and 0, 1, 0, 0. So I'm not done yet because remember I want the kernel of T, not the null space of A. So step 3 is to translate back. So step 2 is to solve. Step 3 is translate back. And what do I mean by this? Well, you know, I have that 1, 0, 0, 0, 0, 1, 0, 0. You know, I'm going to do this on the next page because it's going to get really crowded. So step 2 is to just solve. So any questions so far? Okay, so let's now do step 3, which is to translate back. So I have that, what do I know? I know that these two vectors, 1, 0, 0, are a basis for for the null space of A. And if I apply the correspondence principle, which means going back to this diagram, I go up, I go from R3, I go from, well, in this case, I need to go from R4 to P3. So which transformation I'm going to apply to go from R4 to T3? P3.
PB.
PB, right? The inverse of the coordinate mapping of P. So this is, if it only have the coordinate mapping of these vectors, are a basis for kernel of T. So this correspondence principle is just a translation, right? Isomorphism means same structure. It means it's the same thing with different names. And the things that change the names are these PBs. And now this is, this is the same thing as saying that 1, T are a basis for the kernel of T. So we solved this problem A. So we solved problem A using the correspondence principle. We turned it into a null space problem. And the whole point was these isomorphisms, the whole utility was that they let us go down, solve the problem down, and then go back up without losing anything. So any questions about that?
So when we translate back, we're translating back to P3, right?
Yeah, so that's right, because the kernel lives in P3, right? So when in doubt, when doing these problems, I always encourage people to draw this diagram, because then you don't get confused about which vectors are living in which spaces.
Thank you.
Can you wait? Can you go back
Yes?
to the left side?
Can I go back? Yes.
Can you just explain the null A part real quickly?
You mean step 2?
No, the last leg of step 1.
Oh, okay, good. I'm just using the definition of a null space, right? So null space of a matrix is a set of all vectors so that A times that vector is 0.
Oh, right. Okay, cool. Thank you.
Okay, let me now do part B of the problem. So part B of the problem was to find, where was the problem? Part B was to find a basis for the image of T. So let's do that. Again, step 1 is to translate. Now, step 1 and step 3 are just, they don't require much. You don't have to write this when you solve the problem. I'm just explaining why it's a valid way to do the problem. Step 1 is, okay, R is in the range of T if and only if, well, what's the definition? If and only if T of Q equals R has a solution in, okay, I mean, so where does this Q have to live? This Q has to live in P2, right? Or P3, sorry. But now by the corresponding principle, so this is the definition, this is the correspondence principle. This is true if and only if A times the coordinate vector of Q, the B coordinate vector equals RC has a solution. But now the solution is a coordinate vector living in R4. And do you know how to write that in terms of a certain subspace associated with the matrix A?
The column space.
Yeah, this is just saying R, the coordinate vector of R is in the column space of A. Definition. So that means we just have to find the column space. So step 2 is row reduction. I won't do the row reduction. I'll just get that the column space of A. A was a very simple matrix, right? It was like an easy matrix even by week 1 standards. You can just see that the column space is just the span of the last 2 columns. And now step 3 is to translate back. So therefore, the range of T is equal to the span of these vectors, but not really these vectors, right? You have to translate them back into lying in W. So what linear transformation are you going to hit them with to translate a vector from R3 to a vector in P2?
PC.
PC. Which in this case turns out to be, I guess this is just 2t, and this is 6t cubed. So these are a basis for the range of T, and 1 and T are a basis for the kernel of T. Okay, so we solve these problems by turning them into concrete problems. So I'm running out of time, so I'll skip the theorem I was going to translate. I'll do this next time. Next time I'll show you how to translate the rank nullity theorem. But let me just end by, and I'll talk, okay, I was going to spend more time talking about the point of abstraction, but let me just explain why, you know, in some sense, what have we achieved here? So let me open an image. Okay, so I mean, as I said, we're learning a language where a lot of things are equivalent, right? So what, I mean, in some sense, we've done a lot of little things which all seem maybe not very complicated by themselves, but you know, the point of what we've built is that we have this whole structure, right? So at the bottom level, we have you know, the row picture of matrices. So we have equations. And we have row reduction, and we have pivots. And then we showed that this is equivalent just by sort of shifting your perspective to this column picture of matrices, where we have sets of vectors. And now we have these concepts of span and linear independence. And then we showed that this, if you zoom out, if you change your perspective again, this is equivalent to considering linear transformations between Rn and Rm. And here we have concepts like one-to-one, we have matrix algebra, things like that. And the latest thing we've achieved is we've realized that actually this is related to some very general setting where you look at linear transformations between V and W, and there's a bridge between these things. That's not a very good picture of a bridge, which uses a basis. And now in here we have, you know, we have all kinds of interesting stuff, right? We have polynomials, we have vector space of functions, we have a bunch of other stuff. And so, you know, the point of this language is that just by giving these names very carefully to these types of objects, we have been able to relate quite interesting things at the bottom here to some very concrete things at the top. And doing this, you can actually solve quite hard problems. Okay, like I like problem 9 on the midterm. Okay, so that was the hardest problem on the midterm. I was going to go through it in detail, do it next time. But I don't know. This is how I think of why what we're doing is worthwhile, and I'll give you more examples later. That's it for today.
Professor, I have a quick technical question.
Yes.
Can you see this, a blue X on your screen?
No.
Okay.
Wait, I can see it on my screen.
Yeah,
Really?
we can see
Wait,
it.
wait, where's the blue X?
Right.
Top right corner.
Yeah, top right.
Oh, yeah, I
Okay.
can see it.
All right.
Oh, so you can just like draw on my screen?
Apparently.
Yeah, you have annotations enabled
Yeah.
for everyone.
Cool.
I was just to be able to point out things. It was I just wanted to test that function.
Okay. Yeah, maybe we can use it in the future. Nice. Okay. Okay, cool. I guess I'll take a screenshot of this.
Thank you.
Yep, thanks.
Professor, I actually had a question on the last slide that you had.
You mean the brain thing?
No, the one before that.
Okay. Yeah.
Why is it 6t cubed and not 6t squared?
Oops, that's a typo. Should be squared.
Okay.
Thank you.
Thank you.